It's my pleasure to introduce Laurent Meersseman from Université d'Angers. He's going to speak about moduli problems in a non-Kähler geometry.
Thank you. Thank you very much for the invitation. It's a pleasure to be here. So I will talk about some problems, some moduli problems in non-Kähler geometry. Since it's a stem surface, I will spend some time talking about Kodaira-Spencer theory of deformation, which is my connection with Spencer work. And within its initial form, I mean deformation of complex structures on smooth manifold. Okay, so the plan today is to explain how to pass from local Kodaira-Spencer theory to global Weschmuller flat setting, which is adapted to non-Kähler manifolds. This is really what I have in mind, dealing with moduli problems for non-Kähler manifolds. And then I will talk about an example, and this last part is joined with Lupercio, Katzarkov, and MS. Okay, so let's make the course physics of first modification. I can't resist to do that. Really, the first important theory I learned when I was a graduate student, and it plays a central role in my work. So if we go back to the foundational paper, so it's 68, so the long paper in analysis of math in two parts by Kodaira-Spencer, where they lay down a theory of deformation of a compact complex manifold. So the basic question was to understand when you start with a compact complex manifold X with underlying smooth infinity manifold M. We want to understand complex manifold, complex structure on M close to X. So of course, a good concept to do that, a lot of deformation. So in modern language, let's say it's proper and smooth mapping between analytic spaces with a distinguished fiber isomorphic to your initial X. And usually in analytic theory, you geometrify everything. That's not really important, but simpler to avoid to pass to smaller and smaller measures. Okay. And when you, with this definition, the problem of finding the complex structure close to X boils down to finding a deformation of X containing all the other ones. So of course, the theory culminated in a result by Kodaira in 62 that tells you that there exists a deformation, which I will call Kodaira deformation or rather Kodaira family, deformation of X, which is unique as a germ. And has two properties. It contains all the other deformation. That means that if you have a deformation, another deformation of X, it is obtained as pullback of a Kodaira family by some mapping, some homomorphic mapping. And then you have a minimality, condition amongst all these, usually called complete deformation. And then amongst the complete deformations, you want the most economical one. This is called usually semi-universality, or in the initial paper by Kodaira-Spencer, versality. There are several ways of saying that. First, the most classical one is to say that F is not unique in general. You cannot expect that. But fixing markings of the family, you can expect that the differential of F at the base point is unique. There is another way of saying minimality, which is that the Zariski dimension of K, the base of your Kodaira family, but is minimal amongst complete deformation. Okay, so K, I will call K as usual Cornish space, and curve K as Cornish function. Okay, going back to the paper by Kodaira-Spencer. From my point of view, at least the most important. So they get the definition, they get the setting, they get many important results about deformations. They put many important results. They give very nice example, detailed example. But they also, perhaps the most important point, they give efficient method when you have a deformation to check if it is complete, if it is universal, so it's only universal, etc. Especially, I can't resist to define the Kodaira-Spencer map. So for classical stuff, it's one of my best memory of graduate students. So we just when you take the deformation, okay, so here you have the base. Here this is the base point. You have the family, and then you take a dimension. You take a direction. So with the tangent space to the base. You try to lift to the fiber corresponding to X. So locally, you can always lift since it is a smooth morphism, a projection is smooth. But of course, when you do it in another chart, the lift do not overlap, and the difference between local liftings is something which is tangent to X. So using Church homology, you end with something which is an element in the first homology group with value in the tangent sheaf. And this is the first order, the first obstruction lifting vector width from the base, and this is the obstruction to trivializing your family in the direction. So this is really, I was very happy that I understood that. 25 years. Okay. So now, of course, when you are in a Kähler setting, there is another way of studying small deformation. Of course, related to the first one. You can study small deformations through variation of root structure, period maps, period domains. And in some cases, that allows you to pass from a local theory to a global one, if you have some global theory theory. Sense. Let me put this in a more general context. So, in the context I'm interested in, if you want to study global moduli space, well, one of the basic objects is a Kähler space. So here we call that M is just a smooth, compact, connected manifold, smooth infinite. You assume that it admits complex structure, otherwise there is nothing to say about this. And you look at the set of complex manifolds, diffeomorphic to M, and you look at that, you take the classes up to biomorphism, smoothly isotopic to the identity. So there is another way of saying that. You just look at the pair M with some operator J, some complex operator, the tangent bundle. Let's say it's infinite. Inducing whose square is minus an identity, so inducing a complex structure on the fiber of the tangent space, plus, of course, an integrability condition. So this is something infinite dimensional, but it's much too big. It contains all the complex structures on M. But there is an action of the diffeomorphism group. You can pull back your complex operator. And if you want the Teichmüller space, you don't take the quotient by the action of the full diffeomorphism group, but you reduce to connected component of the identity, so the diffeomorphism that are smoothly isotopic to the identity. Okay. So from that construction, you have a natural topological space. And of course, it is central in Moduli Problems. Well, just a word about that, but I will consider the Teichmüller space and not the full Moduli space. I mean, I don't want to look at the action here of a full diffeomorphism group. For simplicity, if you look at the Moduli space, the full Moduli space, you have more complexity because you have a mapping class group acting on this. And the mapping class group, there are many examples, starting from complex tower in dimension 2, where the action of the mapping class group is very wide. So it simplifies to look at the Teichmüller space. In general, a bit less complicated than the Moduli. Okay, so with that definition, I come back to what I was saying. There are examples, case where everything is perfect. Well, perfect, I don't know. The situation is very nice. T is a complex manifold. For that, it's just a topological space. Huh? E is a complex manifold. You have nice period mappings. So I am, of course, thinking of cases such as the case of curves, of free surfaces, where there are some problems of non-softness. Okay. Hyperkähler manifold, I am thinking of the vibrational Teichmüller space of Verbitsky. So, okay, they're very, very nice, nice example, and very rich. But I would like to do well. My goal is much more limited than dealing with such complicated quite such rich examples. I would like to try to understand how to use Kodaira-Spencer theory to put a complex structure on the Teichmüller space for arbitrary manifolds. So especially I am interested in the non-Kähler case. So forget about variation of structure at this stage. So the basic, very simple idea is say, okay, you take your Teichmüller space, topological space, and you use the Kodaira spaces as complex charts. Of course, it's well known for a long time that this type of work on this degree of generality, especially because you have this phenomenon of jumping of automorphisms. This is when you have a family of complex manifolds, the dimension of the automorphism group of the fibers may vary. Now, perhaps the most dramatic case is the case of F2, the second year support surface. So if you look at its Kodaira space, where is the germ of a disk? And the problem is that, okay, so you have a base point. Base point is F2, and all the other points are P1 cross P1. Okay. So, of course, when you look at that and you look at the corresponding Teichmüller space, well, it's not Hausdorff, it's not locally Hausdorff, so it's far from being complex manifold. Okay, so let me rephrase this in this way because I will use that. You may define your topological Teichmüller space, the function H0, which is just a dimension of the automorphism group of X at the point X. It's another semi-continuous function. So if you want to deal with this degree of generality, you have to use stacks. They are useful to deal with that solutions. So let's do that. So you consider all families above all families of complex manifold diffeomorphic to P1 if it's as always infinite model M. And you look at all families with bases, with any analytic space as base. But take care of the fact that here, since I am working in this Teichmüller setting, I'm not exactly taking any families. I just take families that are obtained by doing deformations through a cycle of biomorphism, so smoothly isotopic to the identity of the fibers. Another way of saying that is that when you look at deformation of a family like that, if you think of that in the infinity categories, it's just a bundle, like that you have some variation in the complex structure of the fiber, of course, in the infinity setting, you don't see this. So this is a bundle. This is a bundle with fiber M, a locally trivial bundle, with fiber M and structural group diff M, and I need to have reduced family in the sense that this bundle structure is in fact given by structural group in diff not. Okay. So it's not very important, but just to stress the difference with the moduli stack. Okay. When you take, well, you construct a category. These objects are all such families over any empty base. The morphism are just morphism of families, above morphisms between the base. Okay. And this T is called T, comes with a projection to the site of analytic spaces. Easy to check that this is category fiber in group with, and then more than that, this is a stack. And so this is a stack over the site of analytic spaces. If you can prove that at least if the function H0 is bounded, it is in fact an analytic stack in the sense, more precise here, that you have an atlas, an analytic atlas. So if you prefer, you have here I is analytic space, and you have a smooth and surjective map to your stack. Okay. Okay, so from my point of view, you just introduced Teichmüller stack, which is just a bunch of all families you want to consider with fiber diffeomorphic to M. Produces a nice categorical structure. You're happy with that. Okay, I am a geometer, especially working in non-Kähler geometry. So I would like to have a much more geometric understanding of that. So a good point with stacks is that from the one hand, you have this categorical description. From the other hand, you have a more geometric way of looking at them.
Sorry, can it happen that it's not bounded? Do you have examples? Or
yes, for the S2 cross S2, so reusable surfaces, you have a dimension of automorphism group. That goes to infinity, in fact. Well, it's not a big problem because you can construct, you can bound this, you can look at the open substack where this function is bounded, and then you can construct sort of inductive limits of stacks. Like some notion of this. So it's not really it's a milestone. Okay, just a warning. Of course, as I explained, Teichmüller space, Teichmüller stack from a certain point of view are easier because you don't have this action of the Latin class group. But you have some peculiarities. The fact that here, when you look at the isotropy of a group of C, you just look at the morphisms with source and target identified. So of course, this is a group of automorphisms. You take a point in T, this is compact complex manifold. We have got isotropy group, is a group of automorphism of this manifold. But since I am in this Kähler setting, this is the automorphism group of so this you just have the biomorphism automorphism of X that are infinitely identical to the identity. So this group is different in general from both the full automorphism group and from the connected component of the identity, because the connected component of the identity here is just the automorphism that are holomorphically identical to the identity different. So there are examples. I gave some example dimension 3 in the same period. And then there is a paper by Katzarkov and you with many more examples, and including examples of surfaces where all these groups are different. Okay. So I want to now to understand more geometrically this subject, this fact. So let us do local geometry. So you fix a point of T, so you just compile complex manifold diffeomorphic to M. And you look for a local atlas. Well, in fact, this is just a rephrasing of Kawanishi theorem. Kawanishi theorem tells you exactly that the Kawanishi family is a local atlas. So, but by that I mean, we don't have but these families define equivalent to having gives you a mapping from K to T, and this is a local atlas. Okay, so that's a nice point. So, okay, you have this categorical point of view of stacks, and on the other hand, you have to think of in a more geometric way. You can think of this as your topological Kähler space with charts modeled on some quotients of the Kawanishi space. But here by quotient, I don't talk of a quotient by group action. Maybe it's a quotient by an holomorphic, by an equivalence relation. Some complicated equivalence relation. So let me be a bit more precise. Quickly, to understand what happens, you look, when you have an atlas, you look to compute its symmetrical way, so you just compute the Kähler product over T. This encodes, so this tells you exactly how it is geometrically. So if you look at this part, when you compute that, this is just some analytic space that encodes all biomorphism between fibers of the Kawanishi family. Of course, as always, biomorphism setting. So in a geometric way, what I am saying is that locally, this defines some morphisms, so you have a source map, target map, and I have to divide K that by this the action of point subtraction by this morphism. Okay, if I do that, I recover the topological Kähler space. Okay. So classically, when you do this type of stuff, I mean, another way of studying them, you can replace the biomorphism by the graphs. So you obtain cycles, and you obtain cycles in a Barré relative cycle space of the product K cos K. Right. Now, if you know all this classical theory by Douady and Barré and others about cycle spaces, you know that there is a big dichotomy between Kähler and non-Kähler spaces. In Kähler geometry, you have many nice properties of the cycle spaces, because you have some compacity results starting from the classical Lieberman theorem. So basically, that tells you that if you have a limit, that you have a sequence of such graphs, if they are bonded, they stay in a bonded part of the component of the cycle space. If you are in the Kähler situation, they will converge, perhaps up to passing to some subsequence. They will converge to a cycle, perhaps a singular cycle, but they will converge. This is the Kähler case. In the non-Kähler case, it's completely false. You have some sequences that, although they are bonded, they stay in the bonded part of the cycle space. They may not admit any convergence subsequence. So this is something I forgot to say. Okay, perhaps I come back. It's really an important point. So when I was talking about Uranishi, I was so okay. I was so excited with the idea of explaining the Kodaira-Spencer map, but I forgot a very important point. Here. Kodaira-Spencer gives efficient theory, so it gives efficient methods to compute the Polish space of any complex manifold. So when you use this, you compute Polish space with Kodaira-Spencer map. There is no difference between the Kähler situation and the non-Kähler situation. If you start from a projective manifold, a Kähler manifold, or non-Kähler manifold, the theory goes exactly along the same line. And if you give me a Kawanishi space, okay, this is the Kawanishi space of manifold. There is no way of saying, but this is the Kawanishi space of a non-Kähler manifold because it has some special pathology. That's not true. Kawanishi spaces can have arbitrary regularities. They can be more reduced at any point. But this already occurs for projective manifolds. So this is perhaps the only theory in compact geometry that works exactly the same way in the non-Kähler case and in the Kähler. So this is something important. Now going back to this Teichmüller stuff, I am saying that when I construct a local atlas for my Teichmüller stack, I will use properties of cycle space, and here there is a difference between Kähler and non-Kähler situation. And a compacity result in the Kähler case, sorry, that are totally false in the non-Kähler case. So now I would like to understand a bit better the geography of this Teichmüller stack, what the type of points, what are the type of local models. I'm very happy with saying it's just some complicated quotient of a Kawanishi space locally. I want to be more precise than that. Of course, I am in a completely general setting, so don't expect a very precise description. But okay. So the first type of points is, I already talked about that. These are the jumping points, just the points where this function of H0, the dimension of the automorphism group, is not locally constant. So I already said that on the Kawanishi space, this is an upper semi-continuous function. This is upper semi-continuous for a standard topology and for the heuristic topology. So this comes from result of power. So when you rephrase that in this context, I am saying that jumping points form a string of properties, if you prefer, analytic subset of T. So in other words, they are bad points, because we already saw that in that situation, the Kawanishi space, as we think of F2, Kawanishi space in a jumping point, it has this nasty property that the same complex manifold is encoded in a positive dimensional subspace. So here it's a dramatic one. If you have P1 plus P1, is encoded in the whole low Kawanishi space minus the base. that you have more complete lower situation, but at each time when you have a jumping point, you have this phenomenon that the same complex manifold is encoded in a positive dimensional steps. Indeed, you have to think of a Kawanishi space as being the best approximation of a Teichmüller space that in the category of analytic spaces. So you want to approximate a Teichmüller space, but it is locally not Hausdorff, or it cannot be an analytic space. So the best approximation is the analytic category, so it is the Kawanishi. Okay, so jumping points are very bad for the local description, but it's not so bad in the sense that they are located in some analytic substack, so you control this phenomenon. Then you have the normal and exceptional points. So normal points, as the name is going to say, that's the point where everything will be nice. Not a very good name, but okay. So of course, you ask such a point to be not jumping. And then you ask for another property. You ask, you say that the point is normal, it is not jumping, and if, when you look at the homomorphism between fibers of K, they are given by elements that are close to the automorphism. So let me draw that. And so you have your Kawanishi factory. Yeah. You look locally, so I have a base point here. Fibers, okay. And then all this stuff is about understanding when two different points of my Kawanishi space encode the same compact complex manifold. Oh. Okay, C'est voilà, just moving. Yes. Okay. But okay. So you have here some S, some T, you have X, it's S, it's T. You want to know when they are biolomorphic. So if you have a normal point, I say that okay, in a sufficiently small neighborhood, when there is such a biolomorphism like that, it's possible that you have such a situation. But phi, if I think of phi as being a diffeomorphism, so I think this as being M with some complex operator, J of S, and J of T. So phi, sorry, is a diffeomorphism between those differential exchange of the complex operator. And if it's a normal point, that phi is in the diffeomorphism group, close to an element, close to an automorphism of a central point. Be careful that I am in the Teichmüller setting. So all these biolomorphism and the diffeomorphism are something isotopically to be identical. So if you may have 2 points that correspond to the same compact complex manifold, but for a biolomorphism that is not isotopic to the identity. In my Teichmüller setting, there are 2 different points. Okay. So this is basically the notion of normal points, and the point which is neither jumping nor normal is exceptional. So this, okay, I didn't give a real definition to the more technical, but this is not very important. This is really the IP. And also, in fact, I shouldn't say it, but yeah, I assume for simplicity that all the Kawanishi spaces that I am dealing with are non-reduced. So we are reduced. Yes. In the non-reduced case, you can adapt all this stuff, but of course, it brings more complexity. So we are reduced. Okay. So now I can try to understand this whole decomposition of the Teichmüller stack between normal points, jumping points, and exceptional points. So there is a well-known fact. It's a nice theorem by Kodaira-Spencer. It's in the third part of their foundational paper I was talking about. I say that the 68 paper is in two parts. There is a third part, which appeared some years later, where they prove the stability theorem. Especially they prove that Kählerness is stable by small deformation. So when I talk about the Kähler case, I mean, okay, you have some Kähler structure, and then you have an open subset of the topological Teichmüller space, or an open substack of the Teichmüller stack formed by Kähler. And for simplicity, let's assume that we are in a situation when you have only Kähler. If you do that, then you can prove that exceptional points form a strict analytic substack of it. So that's good news because, of course, as the terminology is saying, exceptional points, you expect a very weird local model of the Teichmüller stack locally at exceptional points. So you are happy to know that they are located in an analytic substack, so it's like jumping points. Okay, they are bad, but they are located in some strict analytic points. And now normal points, well, since they are complementary to exceptional and jumping points, they form a Zariski open subset of T. And if you look at the corresponding open subset of the topological Teichmüller space, then you can do it with charts of complex Sorby spaces. Okay, by complex Sorby spaces, I just mean quotient of an analytic space by the action of a finite group with a fixed point. Okay. So that's not so bad. Okay, of course, there is a subtlety here. I pass from Teichmüller stack to a topological Teichmüller space, because in a Teichmüller stack you have this, you have the data of the isotropy groups, and there is no reason for the automorphism groups to be defined. But forget about that. Let's say that, okay, what I am saying is finally, if you are ready to throw away the jumping points and the exceptional points, you can forget about all this stuff, and you just have to consider the topological Teichmüller space, and that's nice to say of complex Sorby space. Perhaps not globally on small, but it's not so bad. So remarks, well, to prove that, you really use complexity of space. The fact that it is an OB space, that you have a giant anti-fashion, is a almost direct consequence of Fibonacci. And I'm not happy with that theorem because I really think that there should not exist any exceptional point in this space. Okay, I cannot prove it. Okay, so this is a geography of the Teichmüller stack in the Kähler case. So jumping points, so let me control. So you have a nice Teichmüller stack. You have some analytic substack of jumping points, which can be very complicated. Okay. You have, well, at most, in the worst case, thinking that the conjecture is false, you have another analytic substack of exceptional points. And then if you get rid of that, what you obtain is some complex Sorby space after some reduction process. Okay, so It's a very rough description, but it's general. Okay, let's deal with the non-Kähler case. Of course, jumping points, but it's exactly the same. It's well stuff. It's in any case, so jumping points still for the substack. But what about exceptional points? Well, that's the most annoying part of the talk. Was I have many. Okay, I have two results, in fact, and the most annoying point is that I don't know of any example. But still hope, because I have an example of the exceptional. So let me explain that. Here, it's perfect. We still have the definition of a topological Teichmüller space, and I insist on the fact that you divide this space of this set of complex operators by the action of diff not m, the connected component of the identity in the diffeomorphism. If you put diff m, you have a moduli space. If you put diff plus m, assuming that m is oriented, you have just a moduli space complex structure respecting the orientation of m. But you can, there are other variants. And especially you can define TZ, topological Z Teichmüller space, TZ. So this is the same set of complex operators, complex integrable operators on M. And you divide this time by div Z of M, which is just set of diffeomorphism with induced action in cohomology with coefficient in Z is the identity. Does not act, it acts as the identity. And you can do exactly the same stuff. You can define a Z Teichmüller stack following the same construction. You can adapt the theorem that it is an analytic stack. You can define the normal points, the exceptional. But the action in cohomology is the identity. Okay. So you can define the normal points, the exceptional points, etc. Jumping is the same thing. And if you do that with the Z Teichmüller stack, I have there are examples of the exceptional points. So of course you can say, well, there are examples of the exceptional points, so there should exist also exceptional points. But I warn you that here you have something very special that is not disconnected. Here div Z is not connected. So you don't have this mapping class group I was talking about, but you have a Z version of a mapping class group, which is div Z divided by div not. So you have some non-connected group acting, and okay, it's not exactly the same situation. Otherwise, since I am optimistic, I will say that I conjecture that there are exceptional points in the non-Kähler case. And not only and if you admit that, or if you think that there are some such points, well, there is no reason not to admit the second part, that is that we can fill the whole topological Teichmüller space, because the result I presented before was based on the complexity of cycle spaces, and this is totally false.
What does it feel?
I mean, I just want to say that you can have a component which is pure exceptional. Well, okay, so let me give some results. So I cannot say a lot about exceptional points, but for normal points, you have more or less the same result. Normal points from an open substack. This time it's not very open. And when you look at the corresponding open subset of T, it's not locally modeled on the quotient analytic space by the action of a finite group, but here by the action of a discrete group. That's not a big surprise. You lose the finiteness because you lose the capacity result of now, these results are enough to exhibit some example of Z Tashmiller that are different in the non-Kähler situation. I mean, I can give you an example of a Z Tashmiller stack that looking at the local models, you can say, well, this is the Z Tashmiller stack of non-Kähler forms because of this problem of finite, which is now discrete. Okay. So we have this dichotomy at least at the level of a Z Tashmiller state and Tashmiller stack, Z Tashmiller stack, Z Tashmiller stack of non-Kähler manifold, of non-Kähler manifold is different. Why? Okay. So now let me look at an example.
When you say compact, you mean compactness? Or...
I mean, this type of result, but when you have a sequence, a bonded sequence of cycles, and version subsequence. That's all. I don't know what is the good term for that, but this is what I have. Especially here you have in the Kähler setting where your symmetry group we were talking about subjects natural identification. When you think of it as a part of the set. Okay, so let's give an example. So let me recall you had IBM and the IBM D manifold. A class of non-Kähler. Now this is the part where you can install the okay, so this is a class of non-Kähler manifold introduced by Santiago Lopez de Nebrano y Alberto in 1997. I generalized this construction in 2000, and there is another generalization that I did in 2001. But here I will focus on IBM manifold. I will just recall the construction because it's interesting to remind complicated structure. Just to give a flavor, otherwise with molecular geometry, it's usually not explicit construction. So you start with two integers, n strictly greater than 2n, and you take a collection of n vectors in CR, satisfying two combinatorial conditions, the Siegel condition, you want 0 to belongs to the convex hull of a lambda, and some weak hyperbolicity condition that 0 cannot be on an internal wall. So let me give you a picture to explain that. Where of course I am in the case n equal to 5, n equal to 1. The lambdas are complex numbers, in fact. And there are the vertices here of the pentagon. So I draw the convex hull of the lambda. Single condition is satisfied. 0 is defined. And 0 is not on a segment joining two vertices. This is we can count condition, so this is okay. On the right, well, the single condition is satisfied, but 0 is on the internal wall, so you don't satisfy weak hyperbolicity condition, and you cannot perform the construction. When you have such an admissible lambda, you construct the IBM manifold as a quotient of some open subset of a projective space by an explicit holomorphic action of CF. I just wrote the action to show it's completely explicit. Here the angle just means it's a holomorphic action. And d lambda also can be written completely from the data of the data. You don't get the formula.
What is this angular vacuum?
Yes, this is just this is just so lambda 1 and t. This is just so they are in CM in fact. And this is just lambda 1 1 t1 lambda 1 and t. So this is you start in fact from linear diagonal vector field and you take the flow of n such vector fields with dynamical point of view. I won't get into these details. So this is on this subset V lambda, this action we have proper, and the quotient is a compact complex manifold. And the point is that in the limit case when n so is equal to 2n plus 1, you have a complex torus, compact complex torus, not case I'm interested in. Then in the other case, you have some compact complex manifold that are non-symplectic, non-Kähler, and not in Fujiki classes, so not bimeromorphic to Kähler manifold. So they are really far from being Kähler. Just to mention that to prove this last point, in fact, what you prove is that you compute the Hodge numbers, H10 and H01, and you prove they are different. Okay. Also, just remark when I said I did generalization of what non-Kähler and that they deal with the case n equal to 1, and I did with the case of manifold. Okay, so now just try to apply what I just said to a LDM manifold. I need another notion, which is a notion of stable LDM manifold or LDM manifold in the stable range. So during a long time, I was focusing on simply connected LDM manifolds. It seems more natural to look at simply connected examples. And they also have very different complex analytic property. But in fact, there is a special subclass of LDM manifolds with a big fundamental group, the power of Z, and they are called in the stable range. I won't give the precise definition, but one of the main features of this subclass is that recall that the LDM manifolds are constructed as a quotient of an open set of a projective space by a continuous action, by the action of Cn. But in the case of stable LDM, you can also obtain them as a discrete quotient. So you can obtain them as a quotient of an open subset of C n minus n minus n minus 1 by an action of Z to the power n plus n. And this action is quite easy. It's through diagonal matrices. So it's not very complicated. Of course, you can compute the eigenvalues of these matrices from the lambda. There are some complicated formulas. So you see that even from a complex point of view, they are very different because of this nice discrete description. They are complexifying manifolds in the sense that you have on the class these changes of charts are given by fine and complex transformation. And there are another very nice property that we are in progress, work in progress. We are almost ready to prove with and Ludmil. So the LDM manifold satisfied weak Hodge decomposition if and only if it's within the stable. By weak Hodge decomposition, I just mean that when you look at the Betti numbers and the Hodge numbers, you have the usual equality that the Betti number, say the Betti number K is the sum of the HQ number for P plus Q equal to 1. This is weak Hodge decomposition because I recall this non-Kähler manifold, and HPQ is not equal to HQP in general. And also it's weak. Also the Hodge decomposition is not canonical. So there is no attached structure and things like that. When you try to prove this, you really compute projecting numbers, you compute the Hodge numbers, and at some point you say, okay, very poor. That's wonderful. Okay. So now let us try to apply what I said about the Kähler stack of stable LVM before. To apply what I said about the Kähler stack to the case of stable LVM before. In fact, it's a quite nice situation, which is very, very close to Hopf surfaces. So I have to warn you, because if I say that, you will say, okay, that's just a small generalization of Hopf surfaces. But one of the main features of the LVM manifold, and it is still true for the stable one, is that they have a very complicated topology. So they can have arbitrary amounts of torsion in their cohomology algebra. So I won't give a precise statement many times, but you have to think that if you fix the fundamental group, so we call it fundamental group of this stable manifold, it's just power opposite. So you just fix this power. Then, roughly speaking, the topological classification is strongly related to the combinatorial classification of simply short convex polytons. There are some simply short convex polytons attached to the LVM manifold. I don't have time to go into that. But the point is that they really have a very complicated system. But from the point of view of deformation, exactly well, it's like the case of Hopf surface. So jumping points, there are many jumping points in general, corresponding to resonances between the eigenvalues of the AI. But yeah, in general, contabling, it's a mess. And of course, if you want to, it's almost impossible to get a fine understanding of all these jumping points, starting from dimension 3 and higher. It's too complicated. But if you take this point of view of a Kähler stack and the 3 different types of points from the description, okay, all these complicated points form an analytic substack. There is no exceptional point. And when you look at the normal points, and you look at the normal points that are stable LVM, because, okay, there are also normal points that are not LVM. Starting from a jumping point and deforming a jumping point, you can end up with something which is not LVM. But if you look at the stable LVM normal points, they form an open subset in a topological Kähler space. It has a very simple structure. It's a complex orbit form, so it's even better than what I was talking about complex orbit space. Really complex orbit form. So in a sense, this really looks like the Kähler stack of Kähler points, of Kähler manifold. It's a bit strange, and so. But we are in the stable case. So we are in this case of, okay, they are not Kähler, they're not biomorphic to Kähler manifold, but they satisfy the decomposition. And just a remark to finish. Fine. There is also this essentially an observation, but it's the same thing as in the case of Hopf surfaces. Since you just take the quotient of some open subset of some Cn by some diagonal matrices, you can look at the eigenvalues of these matrices, take the determinant, the trace, or the symmetric function in these eigenvalues, and you can construct like that a sort of an injective Kähler mapping on the substack of normal stable LVM. So you have just an analogy, but you also. Okay, I will stop there. Thank you.
Thanks.